I'm Simon, and today I want to talk about Quiver, a new technique that we've developed for inferring specifications in separation logic. This is joint work with Lennard, Derek, and Michael, who are all here in the audience today. So let's dive right in. Is there only echo for me? Or I will. Over the last 2 decades, there's been a lot of work on verifying functional correctness using separation logic. This includes tools like VST, Verifast, Viper, Iris, and many other great tools. And the reason why they use separation logic is that it's a powerful foundation. It enables modular reasoning about stateful code. What that means is if you have a larger program, you can decompose the verification into verifying the individual functions. And for each function, you provide a specification and a proof. And because this is in separation logic, you can use the specifications to express how the state changes as you evaluate the function. However, while this makes verification of a larger program feasible, it still introduces a lot of overhead. Because if you can see, if you look at this picture, we need to provide a specification and a proof for every single function. And so naturally, people have worked on proof automation in the past, where you provide the code, the specification, and in some cases some additional lemmas, and then you get a yes or no answer whether the function satisfies the specification. And with proof automation, the picture looks like this. In many cases, you can replace the proofs by just checks with the tool. But what about the specifications? In such a compositional verification, you need to provide one specification per function. These specifications can themselves actually be quite large, and so at the end of the day, they also add up. And that's what we want to look at with Quiver. With Quiver, we want to do guided specification inference. What I mean by that is we want to take the code and sketches of the specification. You can think of these as basically specifications, but they're incomplete. They have some holes that we want to fill out. And then we complete them into the full specification by filling out all the holes. All right, so far this is still quite abstract, so let's make this a little bit more concrete. As a starting point for Quiver, we take RefineC. RefineC is a recently developed verification tool for C code. It has been presented here at PLDI 3 years ago. And the key feature of RefineC is that it's automated and foundational. That provides us with a great balance. On the one hand, it has a very detailed semantics for C, and it is implemented in Coq using Iris. And so when you verify programs in RefineC, you get very strong verification guarantees. On the other hand, it uses an automated refinement type system that's implemented in separation logic. And so you get some proof automation, and the programming, the paradigm basically changes to what I showed you on the previous slide. But importantly, RefineC has no form of specification inference. And to see why you may want specification inference, I've brought along a little example here. We have 3 functions, xmalloc, xalloc, and makevec, and they do the following. Xmalloc allocates n arbitrary bytes of memory. It basically wraps malloc from the standard library. Xalloc allocates n bytes of zeros, and makevec initializes a custom vector, a vector filled with integers. And it uses the other 2 functions for that. If you want to verify this code in RefineC, then you need to provide the following specification. You don't need to read this in detail. It basically boils down to a separation logic specification for each of the functions. So xmalloc gives you back some uninitialized memory, xalloc gives you back some zeros, and makevec gives you back a vector initialized with n zeros. Now, that's a lot of specification for such a simple program. In fact, I think it's almost more than lines of code on the slide. So can we do any better than that? One option that you might have in mind is by abduction. By abduction is a compositional and automated specification inference technique for separation logic. Its key feature is really that it's a push-button inference. What that means is you provide no annotations whatsoever, and then you run it on your code, and it provides a separation logic specification for you. And because it's so automated, it has been integrated into the infer bug finding tool at Meta. However, there's a key restriction. It only works on a fixed fragment of separation logic, which includes equality, points to assertions, and list segments. And that fragment is too restrictive for the kind of verification that we have in mind. For example, it's already too restrictive to express the specifications that I showed you on the previous slide, because they contain integers, custom predicates, mathematical lists, and so on. So with our approach, we want to try something different. If you think of the scale between refined C and by abduction, where refined C really provides no inference whatsoever, and by abduction provides you with push-button inference, then we want to be somewhere in between. We want to provide some inference, but we're still willing to take hints from the user. But importantly, we want to do so without sacrificing the expressivity that you get in refined C. And that's what we did with Quiver and its guided inference. So here's how it works. In the first step, you define your logical data types. This includes arrays, lists, buffers, vectors, and so on, whatever you want to work with in your program. Then in the second step, you sketch the specifications. You basically provide specifications, but you can leave holes inside them to be completed. And then in the third step, you run the inference to infer the missing parts. And we do that with a new technique that we call abductive deductive verification that I'll get into later in the talk. So let's see how this works, and we start by defining our data type. To do that, I have the vector example again from before. It's basically a record with two fields. In the first field, it stores the length of the vector, an integer n, and in the second field, it stores a pointer. It's just a sequence of n integers. If you want to define, want to make Quiver aware of this data type, then you need to provide the following annotations. You don't have to read them. They're basically just a definition of a separation logic predicate that corresponds exactly to the picture at the top part of the slide. Once you've done that, you can move on to sketching the specifications. And in this particular example, we really need only one sketch. Namely, we say that at the end of the makeVec function, the result should be some vector. And as I promised you earlier, these sketches can contain holes. So as you can see here, there's a question mark where we leave open which value the vector should have at the end of the function. And then we run the inference. And what the inference does is it infers the same specifications that I showed you earlier. So for xmalloc and xcalloc, it puzzles together the specifications from the functions in the standard library that these are using. And for makeVec, it additionally takes our sketch into account to say, well, the result should be a vector filled with n zeros. All right, so now that I showed you just a glimpse of what the inference can do, let's see how it actually works. And as I said earlier, the key there is a new technique called abductive deductive verification. The idea of abductive deductive verification is that we want to abductively infer preconditions while deductively verifying a program. What does that mean? Well, to a first approximation, we do normal deductive verification. So we have a context here that's a list of separation logic assertions, and we have a goal, which is often the weakest precondition that we reason about. And then we will build up an inference by gradually applying rules. And because this is close to a normal deductive verification, we can reuse the proof automation strategy that's used in refined C to automate our proofs. But of course, there's a catch. And the catch is that we do this in an incomplete context. So we don't only have delta here, we also have an additional precondition R that we want to infer. And we build this precondition up as we go along and verify the program. So let's see what that looks like. And I want to do this with an example. We want to infer that if you have a pointer L that currently stores a value V, that's an integer, and you dereference L and add 1 to it, then you get back V plus 1, and afterwards the pointer still stores V. And to simplify matters a little bit for this explanation, we're first going to start with only the precondition. So we're going to infer that L points to V, and V is an integer, and we will, for now, pretend that the postcondition is just true. All right, to do that, we start with an empty context, and this is the precondition that we want to infer, which I will gradually build up at the top right part of this slide. And as I promised you earlier, we start with some normal deductive reasoning. So for example, the first rule that we apply is we focus on the left side of this addition, because we first want to evaluate what the result is of dereferencing L, and then we want to come back to the addition. Next, we apply a rule for loading from a reference. It says provide ownership of a points to, and then that points to, like, that location is unchanged, and you get back the ownership. But now things get interesting. We need to provide ownership of L points to V, but it's not in our context like it would be in a normal verification. And so what we do at this point is we add it to the precondition. So this is where we do our first inference. We say, well, as part of the precondition, you should really provide this ownership, the points to assertion. And then once we have done that, we can continue with normal verification. The way we do this is we remove this obligation from the goal, we add it to the pre, and then we introduce a new variable r prime that we will infer in the rest of the verification. And then next, we introduce that points to assertion into the context, and we apply a rule for integer addition. Now, once we have done that, there's a new constraint that we find, which we can't prove from our context, which at this point really is just L points to V. We need to show that V is an integer for this addition to make sense. And since we can't prove it, we once again add it to our precondition and continue with the proof. At this point, really only the only thing that's left to prove is true, and so we're done. And we can finish off our precondition by just saying, okay, there's true here. And that is, in fact, the precondition that we set out to infer. Now, that was only the precondition. Remember, we wanted to infer the entire triple, so pre and post. How does that work? Well, we can basically do the same thing, but we need to apply a trick. Instead of doing the inference for the post condition true in the weakest precondition, we do it for an arbitrary post condition phi. And then what we get looks like this. So it has a precondition here, and that is basically the same precondition as we had earlier. But it then also has this constraint. And if you look closely at this, then you will see that this basically corresponds to our post condition here in the triple. So we learn that the resulting value is v plus 1, and then we also know that L still points to v. And really, this is basically a post condition. And what we've inferred here is what is called a predicate transformer specification. A predicate transformer specification is basically an equivalent way of specifying a triple, but you do it with a single proposition as we do here. And Quiver will always infer such predicate transformer specifications for you. So now that I've explained the basic idea, let's see what this can do if you scale it up a little. And to do that, I've brought along the grow function of this vector data type. What the grow function does is it basically, if the length that you want to grow the vector to is larger than its current length, it extends the vector with a bunch of zeros. And I'm not going to go through this proof step by step, and instead only going to focus on a few key points. The first one is that in this example, we really do expressive verification. We verify this code against the detailed C semantics, and that is then also reflected into the underlying separation logic. So for example, this function does null pointer comparisons. It dynamically allocates memory with xmalloc, the function that I showed you earlier. It does overflow-sensitive arithmetic, aggregate pointer operations like memcopy and memset, and it also does pointer arithmetic. Nevertheless, in this particular case, we can get by providing two simple sketches. We basically just need to say that vec, the pointer that we pass in, is a vector before and after the function. And then if we run the inference, we infer the following specification, which basically contains an additional precondition for the second argument, that it should be an integer. It is conditional because the function has two branches, and it also contains the value of the updated vector. In this case, it's the list xs extended with a bunch of zeros. And of course, I want to mention that Quiver also has some limitations. For example, we don't infer loop invariants. You have to provide them manually, like in many other verification tools. We don't infer predicate definitions. As I showed you earlier, you need to define them yourself. And it doesn't support all features of C. For example, we currently don't support floating point numbers. And that's what I wanted to show you in this talk. If you look at the paper, you can find a couple of other things. For example, how to integrate sketches into the inference. We have an adduction engine that automates the inference rules that I showed you earlier. A refinement type system, because as it turns out, when you want to apply this to C code, you need things become a little bit more complex than what I showed you in the simple example. We have a prototype implementation in Coq that uses iris and automatically proves soundness of the specifications that it infers. And we've evaluated Quiver by applying it to several examples. And with that, I thank you for your attention, and I'm happy to take any questions that you may have.
Thank you. So if you have questions, please come forward. Maybe in the meantime, you could say a few words about how does Quiver fail? So what if you don't provide enough input as part of the sketches? So how would you notice? What kind of feedback do you get?
Yeah. So it always tries to produce such a predicate transformer that in the shape corresponds roughly to the code. And then when it fails at a certain point, it says, OK, I will leave a marker here in the predicate transformer that I couldn't finish here. And then when this is shown to the user, they can see, OK, this is where the inference failed. And that marker can then also contain some information of what happened. And semantically, to be sound, we interpret this marker as just false, because then it's still a valid predicate transformer for the specification.
Thank you.
Hi, so there was some work by Ishal Dillig about maximal specification synthesis, or set synthesis using abduction. I was just wondering if you can talk a little bit about the main differences between your technique and theirs. Maybe like what yours, could you apply your approach in that setting to infer specifications?
Yeah, I'm not perfectly familiar with that work, but if I remember correctly, it's pure in the sense that there's no ownership reasoning involved, right?
Yeah, it's not using separation logic, but...
Yes. So many of the challenges that arise in this context is that there's ownership involved in separation logic, and you need to be careful in how you pass that around. And also then pointers and all the pointer manipulations. And that's sort of where the main bulk of this work is basically going to. And in exchange, we have not perfect reasoning for, say, integers.
Hi, Simon. Very nice work.
Thanks.
I have one question/comment and then one bona fide question. So question/comment is your examples didn't have any loops or any such as your
Yes.
loop. So why not just inline? And then it's just a straight line piece of code and you don't write any specifications. Is it, and I'll answer it also, is it because you want to be modular? So you really want these?
Yes.
Okay, so great. That's the answer also. Fantastic. Let me just ask you the question, which is, imagine I'm a user. How would I go about thinking about what to put into the sketch? So this is sort of the flip side of Peter's question of failure. Just I'm thinking, so I know that there's your thing is going to infer stuff from sketches, but can you give me some heuristic or rule of thumb? What should I put in the sketch?
I think often what is very important is that you say which data types you want to use, like the vector in this case, because they are the things that you define by hand. And so the inference will not automatically guess that this is where you want to use the data type. So a lot of the specifications actually contain things like, OK, here's this data type and question mark for the value, because I really want you to tell me what the value is. And after that, I would say, explore a little. Like if you start with a sketch and then you run the inference, and if it fails, you try to provide more information up until the point where you get what you want.
Really interesting. So predicate transformers can be very expressive and effectively the same size as the program.
Yeah.
So can you explain a bit more how do you know you're going to get some abstraction in your predicate transformer?
Have you also brought along your own answer? Damn it. No. The thing that we do to restrict the expressiveness of the predicate transformer is we restrict ourselves to single quantifier alternation, which effectively means at the end of the day, the predicate transformer has all the preconditions of the function before it lists any postconditions of the function. And so internally in the inference, we basically need to resolve those alternations all the time, because at the end of the day, we want sort of an input-output characterization, not something that uses all the expressive power of a predicate transformer.
Thank you.
Thanks.
I think that might have answered my question, but I guess I'm curious, like, let's say I were to throw this at like insertion sort or something, a little bit higher level, and what are the, what's the pre and post condition going to look like? Is it going to be like, oh, you're sorted? I mean, I think you said you don't guess predicates per se, but if you looked at it, would it be like, oh, that's what sorted means kind of thing?
I think what would really be the thing there is that you do need to provide the loop invariant in this. And that one will probably say that you at least have a partially sorted list in some form of sortedness. But then you may still be able to extract sort of the full specification just from the loop invariant. We have one example that's reversing a linked list where this kind of thing happens, where we provide the sort of the strengthened invariant in the middle that says, okay, part of this is reversed and the rest is normal. And then once it gets to the end of the loop, we say, okay, well, this is the reversed list plus an empty list, so really kick out the empty list.
All right, so let's thank Simon again.
Thanks.